So today let's solve this LeetCode hard problem. This is actually really hard in my opinion, so I struggle a lot before coming up with a solution. So I will try my best to explain it, and hopefully I don't make too much mistakes. Okay, so first off, let's talk about the problem description. Basically, in this problem, you are given an array, basically call it boxed, but it's just an array with different colors. So it basically means with different values. So basically you are given an array, and each time you can select a subarray of this array. For example, this is a subarray of this array. And because this subarray, they are all having the value of 2, then I can choose to remove them. So if I remove them, I will get something like 3 square. Basically, it's 3 times 3. So because the size of the subarray is 3, so we can get this 3 squared. So if the subarray is 2, then I can get 2 times 2, which is 2 squared, which is 4. And if the subarray is 1 like this, and I can also get 1 times 1, 1 squared, which is just 1. So given this array, or given these boxes, the optimal answer is 23, and it kind of shows you how to get 23. So let's go through this example. So first you choose this 2 and remove it, and you can see, just like what I have said, because this is the size of this subarray 222 is 3, so this 3 times 3 is 9, so we get 9 points here. And then after getting this 9 point, you can see this 222 is removed, and you can see it becomes 1 3 3 4 3 1. And now it actually chooses to remove 4, and then it will become 1 3 3 3 1. By the way, if you remove 4, you can only get 1 point, because 4 had a subarray size of 1. 1 times 1 is 1. And then we will get to this 1 3 3 3 1 array, and then we can actually pick this. So this 1 3 3 3 1, if we pick this has a size of 3. Again, we can get 9 point now, and then finally there's only 2 1 remaining, because this subarray, then we just choose this subarray, and then we get the point of 4, because 1 1 has a size of 2. So in total, 9 plus 9 plus 1 plus 9 plus 4 equals 23. So we just have to return 23. We don't have to tell how is we gonna achieve that 23. We just need to tell it that the optimal that we can get is 23. So just the point that we have to return. So in our example, for example 2, it's just 1 1 1. So if it's 1 1 1, then obviously we just choose this subarray 1 1 1 as the whole array. So it's just 3 square. So it just become 9. So this is how this 9 come from. Okay, so that's pretty much all for the problem description. Let's see how can we actually solve the problem. Okay, so let's try to analyze the first example to see how can we obtain a workable solution at least. So let's try to read the array from left to right. So basically in this direction. So for reading 1, let's say we are dealing with 1. So what choice do we have? So if we want to optimize the 1, so there's basically 2 things we can do, right? We can either just remove this thing, and then we get 1 times 1, and then we just move our subproblem from previous here to here, starting from 3. So that's one possible way that we can do to remove 1. So another possible way to remove 1 is that now I want to solve this subproblem. Like, now I just want to let the recursion do that stuff. I mean, just let them solve this smaller subproblem and just get the optimal answer of this. And after these things are all removed, then you can see there's a 1 and 1. So basically I can just make 2 times 2 now. So basically it's 2 times 2, 2 square. Okay, this looks like a 1. It's actually a 2. It's so hard to draw. It's so hard to draw on this trackpad. I'm sorry. This is 2. 2 times 2. So why is 2 is because there's 1, 1. It's 2, 1. And then also plus the optimal answer of this section that we recursively solved. So that's basically 2 options that I have seen. So let's look at the second example. I mean the second element, 3. So now what options do we have? Well, again, we can either remove the 3, or we can remove this thing, and then I can kind of get this and this. So I get a 2 square plus this 222. I don't care what is inside that 222. I can kind of get it. Just recursively calculate the maximum of this 222, this subarray. I don't care about it. I only care is that because the next 3 is on these indexes. So I want to remove anything in the middle. So we just remove them recursively and try to calculate the answer of that and get the maximum of this section. Then after it's done, then I can do 2, 2. I mean 2 squared, 2 times 2. So there's another option we have is sometimes we want to have this. So it's not enough to just consider 1 3. We should also consider all the 3, basically, all the 3 on the right-hand side. It's because sometimes we want to somehow sacrifice these 3, even though this 3 can make a match to me, but somehow maybe you can imagine maybe here has a loss of 2, then I would rather sacrificing this 3 and let this portion of 2 merge with this portion of 2. So I will kind of sacrificing this 3 and match with this 3 instead. So that's why it's not enough to just calculate the next 3, but all the 3s on the right hand side. So that's probably one tricky part to think about. You might think, well, then we can just keep a record of left and right, and then we can just solve all the problem recursively, right? Because That's probably the only thing we need to know. However, not necessarily. So if you look at this certain point and you say, okay, I want to like give up or just remove itself from here and move the pointer to the right, then obviously it is okay because there's only one thing in here. So we will just do 1 times 1. However, if we do this on here, we kind of don't know how many 2 that we have used on the left hand side. So it is possible that we only need to know 1 times 1 square, because we somehow didn't consider the previous 2, or it's possible that we consider this 2, so it might be 2 times 2. So once we like kind of just give up the first element and then remove on to the right hand side, for the left pointer, just L plus equal 1. If we do that, then we can, might be possible to do 2 times 2, or it might be possible to do 1 times 1, or it's even possible to do 3 times 3, of course. So that's why only passing L, R is not quite enough. In fact, if we want to remove the L, which is the first one on this range, we also need to know the L underscore count, which basically means how many numbers are already in on the left hand side, which is used for this range. So then we will just know what value to add to the answer if we just choose to shrink the length of the range by 1. So that's why this will be our recursive call. So based on that, that's not the only thing that we need to know. We also need to know all the position of our next element, because as I mentioned before, each element could be a possible answer for us to consider, basically. So after considering all the possible answers, then we can just know for sure that we have considered all the cases. I hope that makes sense. So basically, the time complexity for my solution will be something like O n to the power of 4. Because you see L, R, and L count, they can both up to n. And then for each recursion call, we have to consider every possible next, which could also be n in the worst case. That's why we are having this O n to the power of 4 in the worst case for the time complexity. So I think that's pretty much all for the approach. Let's go through the code implementation. First, just gonna initialize the length of the boxes. By the way, I will call it A because it's shorter and easier to use afterwards. And then, as I mentioned before, we have to kind of calculate every next position of the current array that has the same value of the current index. So basically, you're just returning the next index on the right hand side that has the same color of the current color. So if it does not have anything, I will just return n, which is not a valid index based on how A is implemented, because A is implemented in a zero indexed implementation. So the range of A is just from 0 to n minus 1. So n is an out of bound index. So if it returns an n, so it basically just means that there is no next same element for this particular index. And then I just for each index, and then I will just look for the right hand side. So if there is some value on the right hand side that has the exactly same value as the current index, then I will just say, hey, the closest next same for I is just j, and I'm just gonna break out the loop. And then we can talk about how to do this solve L and R and L count, just pretty similar to what I have mentioned in the approach part. So first, we really want to return the maximum points we can get if we only consider array from L and R. It means L means the left part of the array, and R means the right boundary of the array. So, and also the L count means that there are L count number on the left hand side that are ready to be removed together with AL. So we did that because, like I mentioned before, if we just want to remove, we just want to give up on this AL, then we want to know how much can we gain from removing the current value. That's why we also have to pass on this L underscore count. So by the end of the problem that we just want to return solve 0 and n minus 1. So 0 and n minus 1 is just the range of the whole array, and 1 means that, right, if it removes itself, it's going to be 1. So because AL is equal to itself, so at least the least number is just 1. So first, we're going to check any boundary case. So if L is greater than R, so I'm looking at line 13, by the way. So if L is greater than R, so it means it is not a valid range, then we will just return 0 because there's nothing that we can gain from here. And also, if L is equal to R, it means that in that range, there is only one element inside. So we have no choice but to just remove it. So the way that we remove it, you just use L count times L count. So otherwise, then we can start considering all the possibility. So the first, I just initialize answer as L count times L count plus solve L plus 1 R1. So the first part just means that I give up here and just give me whatever number I can get from removing AL. So the second part means, so now I moved our problem from L to L plus 1. So I don't know what L plus 1 is, but I'm sure that AL plus 1 must be equal to AL plus 1. So that's why the L count is 1. So it's pretty much like how I just initialize it to 1. So let's take a look at the next same L. So if the next same value of the current value is greater than the range, the whole range that we care, so it means that we cannot match anyone in here. So the only possibility for us is to just move the pointer to L plus 1. Otherwise, we're gonna iterate every possible next for this current L. So the way that we do it is that we initialize the next L as the current next L for this index. Then we're just gonna loop through until the next L is out of the range of R. Because if it is out of the range of the R, then we cannot consider it. Because in this solved function, we only care about anything that is greater or equal to L, and anything that is less than or equal to L. So first, if we increase L in this position, I'm looking at line 22, by the way. So if we increase L using this same position, so it means that I want to just somehow in the middle part of it. So basically the next L that is same as the current L will be this next L variable, right? So anything before that and after L plus 1, so after L and before this next L, then I mean just get me the best answer recursively. I don't care what that is. What I care is that after removing this guy, after removing this portion, then I can merge with this next L and make an L count plus 1 to it. So this is how we consider this portion of L. And then, of course, we're gonna take the maximum of all possibility. Then we have to consider if it is greater than the current answer, then we will just become the answer itself. And then next on line 24, then we will just move on to the next same value. In this way, we can iterate every possible same value of L. And finally, we just return the answer, because in here we take the maximum, and then basically we just have consider every possible answer, every possible match that AL can do. So after considering all the matches, then it means that we have considered all possibilities. So that's why this will be the answer that we are hoping to get. So, okay. And don't forget, on line 10, we have to bash this LRU underscore cache. Because if I don't do that, then the problem will be the solution would be exponential. But we add that, it will just quickly turn this whole exponential function into just O n to the power of 4. So that's pretty much everything that I have. Let's try to submit the problem. Okay, that's pretty much all. Goodbye.